So as promised, I want to show you how to do a logistic HLM in HLM7 and talk a little bit about the odds ratios. So I've opened HLM7. Let me move this here, and I'm going to use an existing MDM file, and this is going to be the same data set you will be using in the next in-class exercise. These are data from Thailand, and it's a Thai retention study. And so let me walk you through this. The outcome here is whether a student repeated a grade during primary years, and this is Rep 1. So this is our outcome variable. Now I know that this is a binary variable, yes, no, no for the student not having to repeat it, that a grade during primary school, and 1 for a student who has repeated. So we know that we cannot model this the way it is right now because the standard setting requires a continuous normal distributed outcome. So we have to go into basic setting, and right there it says distribution of the outcome variable, and the standard setting is normal continuous, but we have actually a Bernoulli distribution. So we're going to check this, and then we're going to say okay. And now what you see already is that it's changing a whole bunch of things up here. It shows you that it uses a logit of phi divided by 1 minus phi. That's your eta. Your eta is equal to beta 0. If we're asking for the mixed equation, it will not repeat the the model distribution, the distribution that we're using. It will just start with eta and just telling us that the mixed model right now is an unconditional model. So what you would have seen before would be let me show you real quick. With a normal distribution, it would give you the outcome equal to gamma 0, 0 plus u0 plus r. Now look at what's happening when we're changing this to Bernoulli. We lose the r because remember there is a fixed variance assumed in a logistic model, whether it's regression or an HLM model. So all we have now is that our logit of the outcome is equal to the grand mean plus the variance that is on level 2. Okay, so now we can run this model, but I actually don't want to do this right now. What I want to do is I want to add a level 1 predictor. And so this is male. It's just a direct effect of male on the outcome, and I want this to be allowed to be random. So when we run the analysis, what you will see is, first of all, each iteration is not a line anymore, but they're sub-iterations, and that is due to the binary outcome. So as this is stopping at 100 to ask if I want to continue, it's doing sub-iterations here, and as you can see, for most of these, it's going to be 2, but we're at 100. The other thing you will notice is that things take longer for that reason, and you will need more iterations because you have less information in a binary outcome than you have in a continuous outcome. So I know this is going to come to a stop real soon. So macro iteration 457, and then there are micro iterations, and here we have the output file. So I want to walk you through the output file real briefly. On top, we have the same information that we have, number of units, 7,516 students in 356 schools. We have number of micro iterations. Remember, we had 457 macro iterations, I believe. 456 was the final one that it liked. And then there are micro iterations underneath those macro iterations, as you saw. So there's quite a few more. It tells you here that the method of estimation is PQL. We're going to talk about this next week. And that it's set to 100. That's when it stopped, and it asked us to put a Y in to continue running macro iterations. The distribution at level 1 is a Bernoulli distribution, and the outcome variable is rep 1. Here you have, again, the relationship that is underneath in terms of distribution. Then we have the level 1 model saying we have a beta 0j plus a beta 1j times male, which is linked to eta. And then we have two level 2 models that look just the same as they would if we wouldn't have a binary outcome. The mixed model, again here, as you can see, shows us that we have a adjusted mean, and then we have gamma 10 times male, the impact of sex or gender in this case. And then we have an error structure again that is missing an Rij here because we don't have that. Remember, the variance is set to pi squared over 3. And then we have some information that we don't need to look into too much, but there's a correlation, a covariance matrix, covariance correlation, and some random effects up here. But we want to look at the final estimation of fixed effects of the unit specific model. And this is everything that I'm highlighting here in blue for a moment, and then until it goes to results for your population average model. So those are the things you will look at. Again, you will look at two tables within. The first one is the final estimation of fixed effects. Then you will ignore the one that says with robust standard errors. And then we have a final estimation of variance components. Okay? So what do we see? I want to focus on the male slope on the beta 1. We have a coefficient of 0.45, a standard error is here, and we see that the impact of sex or gender is statistically significant. This is coded that 1 is male and female is 0. What we have here is an odds ratio of 1.58, and you have a confidence interval again. What you see here, the coefficient is repeated in that second half of the table, but this is the odds ratio for being male. What does that mean? That means the odds of repeating a grade in primary school for boys is 1.58 compared to girls. This means there is 58% more boys repeating a grade in primary school than girls. Because 1 is the reference point, so 1.58 is 58% more. So this is how you talk about these odds ratios. Now, it's statistically significant. What I want to talk about next real briefly is the variance components. Remember, you're not getting an Rij. All you're getting is a U0 and a U1. This actually indicates that the U0 is statistically significant and that the slope does not have a significant variance. One thing I want to mention real quickly, because people have asked this would be a situation where you could say there's an impact of sex or gender on the outcome, but there is not a significant variance there in a bivariate model. This is really a bivariate multi-level model. So you could make the argument for parsimony to take this variance out. Also note that HLM7 will just say greater than 0.5. So it doesn't tell us if it's 0.8, 0.9, but it's just so high that it says, okay, the p-value is really far away from 0.05. So that is an argument that can be made. And as I mentioned before, you want to be somewhat parsimonious with your variances because they take a lot of computational time. Let me actually try this real quick. Let me take this model and now take out the random effect. So now we have a fixed effect of male only. And remember, we had 456 was the iteration that this stopped. And what you see now is that this is a way better model because it stopped after 9 iterations. So macro iteration 8 is the one that it's using. We're getting a slightly higher odds ratio here. So there is a change, but this indicates a really good model fit. The thing that you're also not getting in the case of this model is you're not getting a deviance, and that has to do with the way this gets calculated. There's actually a negative a log likelihood function, so we'll talk about this. In any case, this indicates just the number of macro iterations indicates that this is a much better fitting model. So I want to leave it as that, and the exercise in class will go deeper on interpreting odds ratios and then also interaction effects due to odds ratios. Thank you.